use Indo, and for my AMS extended task I did Optical-Flow. So on this monitor I've got a demonstration of what that looks like.
Okay, yep. So the robot is rotating at a constant negative 0.3 radians per second, and then my Optical-Flow algorithm, using the features that it can see, calculates the flow, the distance between how those points have moved, and then on an interframe basis, and then plots that, and it approximates around. It's actually really bad right now. It might not be tracking good points or something, but and then if I people are probably moving as well too, which is going to be making it cry. And then if I do it the other way, so now it's a positive 3, the Optical-Flow will actually track that, and now it's approximating a positive 0.3 radian per second angular velocity. So you could use something like a Kalman Filter, and then you'd be able to get, I think it would be pretty closely approximated. Right now, even this.
How well will Kalman Filter work? How well would it work, based on the assumption of the noise and the noise?
I think it probably wouldn't give you like a perfect representation, but it'd be a lot better. It'd be a lot smoother and like closer to. So what you were asking before, if it has a history, what I do is for every 5 frames, it will calculate the distance and the velocity for each of those 5 frames, and then average that, and then output that average velocity. So it's already like So it's those 5 frames, and then we get rid of the next 5 frames, get rid of it. So it's not like we're constantly stored, because then I think what I had, like, you would probably run into the problem, whereas if you were moving really fast and then you started moving the other direction, it wouldn't map that as quickly because it would have a weighting towards the previous.
Hi, my name is Gabriel, and I'm doing obstacle avoidance for my MSD2 extended task. So originally, I was going to be using the YOLO framework for detecting obstacles, but as Sean has said earlier, it's hard to implement on the Raspberry Pi. So I went into the mobile SSD network, but then I wasn't able to identify this specific block here. So what I did was I went from that to color thresholding, so I can detect the block, so as you can see here. So it can detect so I used HSV to detect the green from the rest of the image. So as you can see here, but since there's still noise, I had to erode the noise and then dilate it back to its original size. Bound the box data to the ROS, which would then translate it from a string into an array. And then I would calculate the distance from the camera plane to the obstacle plane, just the linear distance, but then it would determine where the obstacle was in the camera frame. So what I had to do is calculate. So I know that the frame length is 40 pixels, and I know and so since the bounding box calculates the starting edge of the obstacle from its zero frame, I was able to determine the distance of it from the left plane, I would say. And then I calculated the midpoint. Then I was able to calculate where it was, where the obstacle was in terms of distance. So since I know that distance there, and I know that distance, I calculated where it was there. And that's how I was able to. And then I used triangulation to calculate the distance from each angle from
James Fry, and I have implemented dynamic obstacle avoidance on the TurtleBots. My project is designed to work with any configuration within reason of obstacles within the workspace and is capable of navigating to a set point from anywhere within the workspace. It's currently set in simulation for a 2 meter LiDAR scan, not quite as realistic in hardware, but it works well in Gazebo. Every 1 meter it will stop and rescan to adjust for any obstacles that were not within its range or ones that have newly appeared. I can't actually do that in Gazebo. It tends to have a crash and be very annoyed whenever you try and delete or change things halfway through.
So what are we actually doing with the LiDAR? What's that?
The LiDAR is being read into the occupancy grid seen here, which is then inflated, and PRM is used to create a path, which the robot will then follow, as seen currently in the simulation.
So what's the blue cloud?
The blue cloud is the PRM adjusting itself until it finds enough, until it creates enough nodes to actually be successful. It tends to want to create a huge number when there is a lot of blank open space, actually far more than when there are multiple obstacles. So it is currently rescanning the path, and then the probabilistic roadmap will update to account for the newly detected obstacles and also remove any that have vanished.
In our practicals, we were actually doing a sensor fusion of ODOM and Python as well. But the design of this filter is it's supposed to help in increasing the accuracy of that sensor fusion. And the ODOM and Python values are fused in the filter, and then you get the control inputs, the state equations, and the measurement update equations that I'm using. This is basically the three equations for x, y, and theta for the mathematical model of the TurtleBot. And then you use delta x, delta y, and delta theta, which are the change in the encoder values when the robot moves, and you use that to update your measurement estimates. And your control inputs are your wheel linear velocity and your wheel. So basically the EKF estimates are now just really close to the Vicon estimates.
Yep.
So the Vicon estimates are treated as the ground truth, and the EKF graphs, which are the brown, blue, and the red, they are kind of acting like they're smoothing out the errors in the Vicon data. So that's what the EKF is meant to do.
Basically, what we're doing is reducing some of the uncertainty present in the Vicon and odometry data. So for the odometry uncertainty, we calculated that in the previous practical. By doing measurements, and then the Vicon uncertainty was given to us. As noise has been added to the Vicon, because usually it's pretty precise, but they knew exactly how much noise. So process noise is basically what the Vicon, the error in the Vicon. I think I had it as the odometry, but it made the results really offset. So I made it the Vicon, and yeah, so basically what was happening was the EKF and the Vicon were like offset from where it should be. So I'm using the Vicon for the process noise, and then the measurement noise matrix here is basically just the Vicon and then the odometry covariances.
Doing dynamic obstacle avoidance using vector field histograms. My code is essentially going to start at the point where the robot is now. It's going to drive to around about here about, and then it's going to drive back, and I'll change like the obstacles as it goes along, and it should be able to navigate its way. Each of the LiDAR scans is taken in, and it turned into a histogram, and it determines which spaces are free and which spaces are not free. So if you would look at this and say, oh, there's an obstacle here, don't go that way, there's a space out here, so steer more towards that direction. In terms of my angular velocity, I have a linear relationship. I set the maximum speed when it's at pi to 2 radians per second, as I thought that was I did some like testing of like different speeds, and that was the nicest one. It wasn't too fast or too slow. I measured the radius itself and kind of estimated. I measured it from kind of about the front of the LiDAR scan to the back corner, and I got like a 0.2, so I set that as my robot radius. And then for the safety distance, I added another 5 centimeters onto that, just to be safe. So I'll just change that.
Does it detect obstacles if it's only one block wide, or do I have to do two blocks wide?
I can do 1 block wide. Can I say if you listen out to it? Yep.
Human tracking and also isolate that human amongst a group of humans and follow that particular person with the block. So you'll see these lovely purple socks that I'm about to put on, and that's the colour that I'm using to track that. Follow me, stop when it gets too close.
Can you explain how exactly you detect it?
Yeah, so I think it's going to be all lovely hands. Actually no, this is an issue. I'll explain that in a bit later. What I'm doing is using a convolutional neural network to detect human, and then I'm reconstructing the bounding box outside of that human, checking for the number of pixels that are of their own colour. If there's a certain number of those pixels, then it will follow that person. So if someone else were to jump in, it shouldn't follow you. So yeah, that's the idea, that it just follow me around. If I jump out and James is going to jump in, hopefully it doesn't follow you. Good. An issue I am having yep. So if I jump back in, fine. And so yeah, back to the bounding box. It'll take the start and end location of the X position of that bounding box in the total field of view of the camera. Add it together, divide by 2, and you get the midpoint of that bounding box. And if it's less than 200, it'll turn to the left. And greater than 200, turn to the right. There you go. The only issue I'm having is that the robot, if it sees, if the robot isn't seeing a human with a certain number of pixels, then it won't send any data, which means that it's going to stay currently staying on whatever the last image was. That's why it's currently turning. So if I were to like jump here and then jump that quickly, the bot will keep going, and so I need a timeout thing on that left side.
So my project is basically human following based on the colour of t-shirt that I was wearing, and I showed green for this. Two scripts on Python on the TurtleBot, which first one does all my basic video operation with the mobile net SSD cafe model. We pick up a human, which we arrange these. So basically made it so that the robot will only detect people out of all the objects that it can, so don't worry about bottles, chairs or whatever, we don't care about them. And then I've done some HSV thresholding with green. So I stick my shirt in front and it'll try and follow me because I thought I was wearing it, but I'm not. Ugh. So basically it uses the HSV threshold and it's lost me, so it's circling. And I create my bounding box about every person, and then a new bounding box around the body area. basically to calculate how many pixels are green in that area, and if it is enough green above the threshold, it will start trying to follow me based on where I'm standing. So the angular velocity is based on my midpoint of that bounding box. I just use the linear relationship between that. And the distance is another linear relationship based on the area of that box to show how far away I am. So obviously, bigger bounding box, you'll think I am closer. So if I spread my arms, it will go away. It thinks I'm big, close. Back. Forward again. As you can see, it's really slow. That was main limitation because of the camera itself. As it's driving around, the FPS gets pretty low. So if I walk away, if it's turning too fast, you won't have enough time to actually find me. And also on the left side, it isn't very nice because I can't. The frame is supposed to be 300 in the Y and 400 in the X. The webcam doesn't let me use the 400 in the X, it lets me only use the 300. And so the 300, 400 side pixels is on the left side, or the right side of the robot's camera. Scripts communicating through a socket. Mobile net, SSD, with cafe model. So the cafe model is the train network.
What's the frame rate? What's the scene time?
With one person, it's roughly 5 FPS. We introduce a few more people. As it's calculating pixels, it gets really slow, probably under 1 sometimes. Yeah, so it can get really slow.
Obstacle avoidance, but using machine vision and purely the camera as my mode of detecting an object. As John spoke about, we're using the neural network computer to run a convolutional neural network to decipher between a lovely healthy bottle of Pepsi and a car in real life. So the idea is, with it being dynamic, the car can be driving along and the bot follows the car. You put the bottle of Pepsi in front of the bot and the bot will drive around it and continue following the car. It's showing a frame of the camera and it's showing that it's got a bottle detected and the car is detected. We run color thresholding, so the bot will only follow a purple car, and we've cross-tested this with other color cars and it works. I just need to work on my wavelengths a little bit. And then it picks up the car again and off it goes. So the idea is, if I had a bit more time, I would obviously refine my waypoints a little bit, and if the car was still driving, it would pick up the car again and continue on the car. The car's location with reference to the X and Y coordinates of the robot's location using the Vicon. There is, at the moment, we've just got half a meter added on, just for roughly the bot and car will always be half a meter apart-ish. And then I've split it up into the 4 quadrants, so it should be pretty repeatable in any angle. And then we've just worked out a rough distance using that measuring board at the back there, worked out how far the car is versus how many pixels we can see, and then that is just a linear speed controller between that. Then from the waypoints, it will actually dynamically set this X2 and Y2, and so they're roughly, if we say the bottle is a couple mil big, we put a bit of an inflation distance on that, just so it'll make sure it gets around it. And then it'll pick up the last car location, and then that being the last waypoint it should drive to. So pretty dynamic in the sense that the car can be anywhere within the Vicon. We can run the test in any angle, any direction, and it should, in theory, with a bit of buffering, work.
What happens if you go 2 cars?
That's why we use color thresholding. So if there's 2 cars, we've actually set the color count to be more than 400 pixels in our bounding box, and I had a green car and we tried it and we didn't follow it. So Yep, nailed it. So I was trying to turn this way. If I move that, stuck now. But yeah, if it was coming this way, it would obviously turn to the left, and off it goes. So we split, kind of similar to John's, I've split my bounding box in half, so it senses the bottles on the left-hand side. It'll turn to the right to get around it, and vice versa. And obviously set the waypoints dynamically for what its phi orientation is, where the bottle lives, how far the car away is. So a lot of
it depends on what it sees, what it
yeah,
sees.
yeah, and in what position it lives. So in theory, it should follow the bottle around pretty well.
Does it have any kind of memory? So if the car goes out in front, does it remember what direction it was going in each time?
That was what was going to be next to make those waypoints a bit nicer. At the moment, it's just a repetitive update, and I can't latch that last bit. But once I know how to do that, it should be
That's cool.
pretty easy. But yeah, it follows pretty well.
So as long as the car doesn't move too far out,
Yeah,
so it's out of the speed.
it's about a minute